Hello, welcome to Utilizing LoL Drivers in Post-Exploitation Tradecraft Talk. My name is Bariş Akkaya. I work as a red team engineer at Pico Security. You can find and DM me on Twitter for any questions or just a chat. Let's see our agenda today. We are going to take a look at some of the motivations and challenges of kernel mode attacks from the perspective of a red teamer. We will analyze several capabilities of a driver, which can be functional for red teamers in post-exploitation phase. We will try to implement a couple of TTPs with this driver. We will also look at protected processes and ways of interacting with them. We will create a simple meta-operator loader, which uses a protected process to evade defensive measures with the help of a driver. And in the end, I will introduce a tool that can be used to simulate the techniques in this talk. Let's begin. Current offensive security practices mainly focus on user mode threats. When we think the variety and importance of user mode threats, it seems only natural. Defensive products are also aligned with this trend, since it's usually harder to detect and prevent a kernel mode attack. However, threat actors continue to use kernel mode attacks for different purposes. We can ask why an attacker prefers to use a technique, including something like installing a driver. Well, as we said, evading defensive measures is one of the main reasons. Also, executing code in the kernel gives an attacker the ability to bypass user mode controls like access control lists. Another reason could be manipulating operating system or AV components in itself, since these parts have generally restrictions in user mode. Since we are talking motivations of using kernel mode, let's see an important defensive mechanism frequently used to detect user mode attacks. API hooking and its bypasses were very well studied subjects in last years. API hooking can simply be defined as changing behavior of API calls. Windows has a compartmentalized architecture, which depends on lots of calls between separate layers. So a hooking function would act as a man in the middle between layers, like an API call from ATDLL, and it can read or change parameters of that hooked API call. This technique is used by defensive products to monitor behavior of a process and detect its malicious patterns, for example. Currently, attackers have several options for dealing with that. One of them is unhooking by using a fresh copy of that library. Attackers also change API calls with their direct syscalls when compiling a tool in order to evade API hooking. There are also lots of techniques, depends on Windows security flags, which could be used by an attacker to defend its process against AV's hooking engines. So, what prevents attackers just using kernel mode to execute malicious code on their target systems? First of all, it's difficult to create a stable rootkit because new OS versions may have different undocumented objects and mechanisms which affect the stability of malicious driver. Secondly, you need to have administrator privileges on the target system to deploy a driver. And although you have it, you still may choose not to deploy drivers, since it can alert various monitoring tools. Lastly, Microsoft tries hard to defend kernel space against malicious codes with restrictions like driver signature enforcement and patch guard. Driver signature enforcement is one of the restrictions for new developed drivers. These drivers has to be signed by Microsoft itself. This procedure requires an EV code sign-in certificate, and it requires also a couple of other steps. Windows Patch Guard is the feature that prevents the patching of the kernel code. According to Microsoft, the quality cannot be measured on a dynamically patched code in kernel, which affects the whole system actually. This feature has affected both rootkits and antivirus applications operating in kernel level. That's been said, there are still bypasses for DSE and patch guard using vulnerable drivers, which can provide kernel read-write or code execution capabilities to bypass DSE is a fairly studied subject. You can find great research articles on this subject, actually. Okay, we can ask, are there any other drivers that we can use for offensive purposes? If there is, we may not need to develop rootkits from scratch, and we may not bother to bypass driver signature enforcement or patch card, which may cause blue screen on new Windows versions. While I'm looking for a driver like that, I checked Process Hacker, which is one of my favorite tools in Windows. I always thought about using it in terminal, but I could not find a decent port of it. To whom knows nothing about Process Hacker, it's a Windows monitoring tool with very nice features like reading memory of a selected process. It can make your life easier when you try to reverse something or understand the behavior of a process. In order to extract data from the system, Process Hacker deploys its own driver and uses it for interacting with other processes. It has abilities like killing protected processes, reading system handles, which makes it a very powerful tool. It has also been used by malware families like Tradecraft in a simpler way to kill AV processes before. So I began to read the source code of Process Hacker to understand how it communicates with its driver. Process Hacker uses IOCTL calls to execute some of its tasks using the driver. IOCTL, or input-output control calls, are a way of communicating with the device drivers from the user mode code. A process can send IOCTLs to a driver with control codes, usually specific to that driver. According to the control codes, driver executes specific tasks and may return an information to the process. Windows gives an interface for IOCTLs with device IO control function, which also uses anti-device IO control file function in NTDLL. Here we can see the Process Hacker's code, which sends an IOCTL to its driver. Functions starting with KPH in the source code are wrappers for sending IOCTL to driver with specific codes. We can see this function sends the code which is assigned to KPH query information object. We can find IOCTL codes mapped to these names in the Process Hacker source code. These IOCTL codes can make the driver execute its regarding tasks. We can see the IOCTL code for KPH query information object is 151. So when we send IOCTL with 151 to Process Hacker driver, it executes the task mapped to that IOCTL code in the driver. The source code has lots of IOCTLs that can be useful for an attacker to execute in an engagement. However, after reading the code from the driver part, we can understand using some of IOCTLs is actually limited to just Process Hacker process. You cannot send these IOCTLs from another processes, so they are protected. Process Hacker driver has a client verification mechanism for the functions that can be used maliciously by attackers. A key is generated in the verification process when the driver is installed to the system. To generate such a key, driver checks the signature and the image of the process, calling the IOCTL first time with its own key. So if the client process is verified, a new key is generated to be used in IOCTLs like, let's say, KPH open process. Finding out the client verification mechanism explains why I cannot find a terminal port of process hacker. Since I don't want to deploy entire application to the target system in an engagement, I checked when the verification mechanism was implemented. We can see from the commit messages that it was implemented in 2016. To check if I can send IOCTLs without verification, I downloaded an old version of Process Hacker. I saw that I can send IOCTLs to all driver without using Process Hacker binary at all. I also want to check the code from the old version. After reverting the repo to the old commit, I can find the same header file with IOCTL codes, which are shown as reserved in the current version, like KPH write process memory. We can see these functionalities are removed from the current version of the driver, possibly because they could be abused easily. After finding this header file, I began to test simple functions using the driver. For the first implementation, we will see how can we read process environment block of a remote process by using Process Hacker driver. Normally, reading PEB consists of 3 steps. Opening process handle using anti-open process, querying PEB address with anti-query information process, and reading the memory using anti-read virtual memory. These API calls are dispatched in the system service dispatcher, and after execution, it returns proper informations to user mode processes. In order to use Process Hacker driver for some of the API calls, we can change anti-open process to anti-device IO control file with open process CTL code, which has 50. We can also change anti-read virtual memory to anti-device IO control file, since the driver exposed the same capability. These API calls causes IO request packets to be sent to the driver, which will end up executing the function defined in the header file according to its IOCTL code. This is the code implementing the reading PEB using Process Hacker driver. KPH connect is the function used for getting the handle for the driver device object in order to send IOCTLs. By using KPH open process and KPH read virtual memory, we can see we open handle of a remote process and read its memory using this driver. Actually, it is the Process Hacker driver execute these tasks and returns information to our client process. So let's see the execution of our implementation on a virtual machine. This is the old Process Hacker driver we downloaded for using without client verification. We can see it's signed under the name of the developer, Process Hacker developer. We can install this driver using Service Control Manager, Service Control Manager configuration tool, sc.exe. Okay. First, we see the execution of binary compiled with standard API calls. We can see PEB of a process it's actually the process, Elsa's process, is we can see the PIB of a process is read from the address in the command output. Secondly, we execute binary compiled with kph functions using process hacker driver. We can see the difference of, okay, so to see the difference between these two, we can use a tool like API Monitor. API Monitor is a tool that you can use to hook API calls of a process and display the function parameters in real time. You can check the APIs that you want to hook from here and select target process to monitor. You can also start new processes for monitoring. We check anti-open process, for example, to hook. We also checked anti-read virtual memory for hooking. We also check anti-query information process to hook our new process. Last, we checked the anti-device IO control file calls. Then we start executing our first binary, which uses normal API calls. We can see process ID with 680 is opened from API parameters. We can also display the buffer read with anti-read virtual memory call. Yeah, we can see it's the remote process is opened, and we can see the buffer is actually read. To compare second binary with this, we execute our second binary using API Monitor. As we can see, two of the API calls are changed into anti-device IO control file call. Doing that, we have tested that we can alter the execution flow of a simple program by using IOCTS instead of standard Windows APIs. We can also display the buffer sent to process hacker driver using API Monitor, like here. Okay, what are the advantages of using IOCTS instead of standard Win API calls? I think this creates an execution path which is harder to analyze just using API hooks. Since defensive products tend to hook API calls like virtual allocax, write process memory, and create remote thread that are frequently used by malware families and offensive tools, switching these functions with IOCTLs would create a non-standard behavior. Also, the IOCTL codes are usually specific to the driver, so an automatic analyze just looking at the IOCTL parameters would be hard for EDRs and also sandboxes. Secondly, process hacker driver uses kernel mode when it opens a process, so that it bypasses user mode access checks. This is the main reason that process hacker can display so much data. Actually, normally a process wouldn't be able to display. By using IOCTS, we can utilize the same capability with any tool. One more important thing is that modern day antivirus programs uses mini filters to register into kernel notifications like process or thread creation. However, they can be more reluctant to analyze notifications coming from kernel mode operations. Therefore, it's possible that some of the tasks executed by process hacker driver can execute without notification of antivirus applications. The main reason behind this capability, which can be abused by attackers, is that it deliberately ignores some security check on behalf of functionality. Microsoft has the documentation for driver developers mentioning this type of issues when managing handles in kernel mode. Disregarding proper handle management could be an indicator that a driver could be used as a leverage to bypass user mode access controls. So we can identify these drivers as low drivers. Although changing standard API calls to IOCTLs seems easy to implement for simple usages, rewriting offensive tools which have various capabilities could be problematic for a red teamer. Also, you won't have access to the source code of every offensive tool. It's necessary to modify the tools to use IOCTLs. For this purpose, we can use API hooking, this time for changing execution of our own offensive tools or processes. By using a hooking library of your choosing, you can redirect your API calls to sending IOCTLs to process hacker driver. Here we can see an example of using Microsoft Detour library to hook open process and read memory API calls to redirect them into KPH open process and KPH read virtual memory. This code creates a DLL which can be injected into your attacker process to hook the API calls. Let's try this method on a well-known tool. In this demo, I will try to hook Mimikatz to make it use KPH functions when it dumps the credentials. Normally, Mimikatz uses open process and read virtual memory calls to open Elsa's exe and read its content. We start monitoring Mimikatz process by using API monitor. We can we can see NT calls are made here. We can also see NT read virtual memory has returned the contents of Elsa's memory in parameter. Okay, we restart Mimikatz process again for this time hooking. I will use process hacker's own inject DLL feature to inject our detour DLL into Mimikatz exe process. We can see that we choose our detour DLL. So we can see that our DLL is executed and it's successfully connected to the process hacker driver. We start monitoring Mimikatz process again. We choose NT device IO control file from API monitor to see IOCTLs. When we dump credentials from Elsa's process, we see that the API calls of NT open process and NT read virtual memory is not shown in monitored calls. This is because DLL we have injected actually redirected Mimikatz code to use KPH equivalents instead of Win APIs. To see IOCTL code, we start monitoring again. We again dump the LSAS process. Now we can see all IOCTLs that is used by Mimikatz process for opening LSAS and reading its memory. This way, we can modify tools without actually recompiling them from scratch. Let's look at another implementation of our LOL driver. In summary, process injection consists of 3 steps: allocating memory for the payload, writing payload to allocated memory, and executing the payload. To inject a process using the LOL driver, we can utilize some of the IOCTLs. This is a simple code, hijacks the main thread of a process to execute a shell code. To do that, you need to suspend the thread you want to hijack after you wrote the payload into the address space of the remote process. Then you get context of the thread, which includes registry values. Since it's suspended, we change the RIP registry to the beginning of our shellcode by using setContextThread API call. After resuming the thread, we expect that our shellcode is executed. We can implement the same behavior using process-hacker IOCTL functions. These are the IOCTL functions that are used for the same functionality. Since there is no anti-suspend thread equivalent for KPH functions, I used KPH suspend process and resume process functions instead of the threads. After switching API calls with their equivalent KPH functions, the injection code becomes like this. Let's see how it works in the demo. In this demo, we will inject a shellcode into explorer.exe process by using thread execution hijacking method. Here are functions checked for API monitoring. Let's start our first program, which uses standard thread hijacking code. After execution, we see that the calculator is spawned. We can see the anti-DLL APIs called by our program. Most of the defensive product would identify this as thread hijacking because it's a well-known pattern. Now, let's check our implementation using the process-hacker driver. After a couple of seconds, we can see the shellcode is actually executed. When we look at the API monitor output, we can see anti-device IO control file calls in place of the old Windows API functions. Our LOL driver does not have an equivalent for virtual unlock, so we can still see it in the API monitor output. We can check we can check the old API calls kind of normalized from the perspective of analysis. This version, actually, new version is harder to detect as a thread execution hijacking than the standard one. Okay, let's move on to protected processes. Protected process Lite is a Windows feature introduced in Windows 8.1. PPL is a feature of a process defined in one of the fields in eProcess kernel object. Windows provided as a boundary between OS components and user applications. One of the well-known usages is running lsas.exe as PPL by configuring it with a registry key. If a process is started as PPL, opening handles with full access is not permitted, and the access right will be masked to lower according to its PPL level. PPLs also have a hierarchical level system between each other. As it is shown in the graph, a PPL process with Windows TCP level can open full access to all other PPL processes, while a process with anti-malware level can only access fully to processes with the same level or below. As we said, PPLs usually used as a mitigation for credential dumping attacks. There are studies on turning off PPL bit by exploiting vulnerable drivers to override the field in eProcess objects. Although this is an effective method, it can also create an indicator for defenders as well. Moreover, driver exploit may need to patch some objects in the kernel, which can be problematic for patch guard in different Windows versions. There may be different ways to interact with PPL processes, and since we can open handles using our LOL driver without any restrictions, it may be possible to use PPL as a protection for our offensive payloads. Creating a process with PPL is possible only if you are using a PPL signed executables. These executables also be can be also third-party programs like antivirus executables, but third-party executable can be signed as anti-malware level at most. I want to create a host process for my offensive payload at Windows TCP level because it's higher than the anti-malware level. To do that, I check the Windows TCP PPL signed TCP level PPL signed executables in Windows 10. I decided to use services exe as the host process. After that, I created a simple loader for using early bird injection technique to create a new services exe instance in suspended state and injects it with our payload. Since we have the driver of process hacker, we use it to open a full access handle to create a services exe instance and write our payload with kph write process memory. After sending an APC to execute our shellcode, we call kph resume process to start our execution. This is the source code of the loader that we designed. As we can see, it utilizes kph wrapper functions to get handle and write payload to PPL process. Let's see how it works in the demo environment. This is our demo environment for the loader. As we can see, real-time and cloud-delivered protection is on, and also the Defender is updated. We can also see Elsa's process is also configured to be run as PPL. Let's try our very first demo that reads PEB of Elsa's process with standard API calls. We can see it fails as we expected, since opening handles to Elsa's is restricted with standard API calls. Okay, let's create our payload. This is the attacker Kali machine. We create reverse HTTPS metapreter payload using MSF Venom command. We also start our metapreter handler since I intend to serve the first payload on a simple HTTP server. I encrypted the shellcode using a simple IS encrypt mechanism. We start our HTTP server on the attacker machine. On the target machine, we execute our loader with URL parameter to downloading the shellcode. As we can see in the process hacker window, a new services exe instance is created with system token. We check the PPL level of it, and it is shown as the WinTCB level. Now turning back to attacker machine, we can see any metapreter session is started. We can check the current user and the PID of the process. Okay. Let's try a different thing. We said anti-malware processes have lower PPL level. So in theory, we should have enough privilege to inject into the defender process from our services exe process. We can use migrate command to inject into defender process like this. We check the process ID. And also we can use, since we are in the defender process, we can use well-known malicious tools like Kiwi inside the defender process without facing any obstacles actually. Let's dump credential from Elsa's exe, which is configured to run as PPL. When we execute the command, hashes are dumped without error. Okay, that's all. I decided to gather these techniques in a tool called Offensive Process Hacker. If you want to check the techniques I mentioned and some others, you can find it on GitHub link. It's a new tool, so pull requests are always appreciated. For next, I plan to search for drivers which can be utilized similar way. I intend to implement new techniques to offensive process hacker as well. Also, finding less noisy ways of installing driver would increase the impact of this project. That's all for this talk. Thank you. See you in QA.